Thank you for staying tuned to the part 3 of Inclines 3.08. You've been very patient, and your patience will be rewarded with this example. This complicated example looks at two masses being tied by a string, hung on a pulley, and placed on an incline. So what happens if you get something that looks like this? How do we break this problem down? So, first things first, we gotta draw a free body diagram. Let's take a look at our two masses, okay? We got two things. Let's draw a free body diagram, starting with this mass over here. So he's got the force due to gravity acting on him. So I'm going to label this as mass 1, and I am going to label this mass number 2. So I'm going to call this Fg2 as a result. So Fg2 is acting on this object, the gravity of it, and also tension in the rope, assuming it's massless. On the 6 kilogram block, you have the tension acting on this guy. You have, based off of inclines, you know that there's a normal force acting on this. And you know that there's also a force due to gravity acting on this one as well. I'm going to call it Fg1 because it's the weight of mass number 1. So here we got the free body diagram. Next up, we will need to look at the direction of acceleration, which is up this incline and then down on this side with the pulley. Now, because we're dealing with an incline in this case, we're going to have to adjust our axes for the first mass, a 6 kilogram mass. I'm going to look at up along the incline as my x-axis and perpendicular to my x-axis being the y-axis. Next up, I'm going to resolve Fg into its components, Fg1. So I have Fg1 going down over here. So this is Fg1y. And then I have going along this direction over here, I have this is Fg1x, which I'm going to write over here, Fg1x. Okay. We also know that the angle is 35 degrees, which tells us that this angle over here is also 35 degrees. Now, if we want to write our Fg1y and the Fg1x into their expressions using Fg1, we can do that. So looking at the Fgx, the Fgx is the opposite side of 35 degrees. So this is Fg1 sine of 35 degrees. For Fgy, this is equal to my Fg1, and because my Fgy is the adjacent side, this one is cosine of 35 degrees. Now I have broken all of my forces into their components. The first question is, how do I know which direction my object is accelerating? Is it accelerating this way, or is it accelerating the other way? And how do I figure it out? Which force is stronger? So in this case, you may think that, okay, well, I need to compare Fg2. If this weight of a 4 kilogram mass is larger than the x component of the 6 kilogram weight, which is our Fg1x, then that means Fg2 will win. Or maybe Fg1 will win, depending on which force is bigger. So, do we want to calculate this out? You could do it. However, there's always a shortcut. No, well, not always a shortcut. But in this case, what you could do is make an assumption. And you might be thinking, what? How can we make this assumption? Because at the very end, when you calculate the acceleration, you may get a negative value. If you get a negative value for acceleration, you know that the objects will be accelerating in the opposite direction as whatever you assumed. So I am going to assume that my whole system is traveling towards the right, traveling down on the right. So this is my assumption. So I'm going to assume that my whole system will be going down on the right. So I am going to use that to calculate the acceleration of the masses. I am going to look at that blue line as my direction of acceleration. So I'm going to look at my F net. And my F net is going to be my M total, because what I want to do is I want to use my entire system as both of my objects as my system, because this is going to help me find the acceleration of everything, because I don't know the tension forces. So it's very similar to your tension problems with multiple masses, except we're just dealing with an incline. So if we choose our whole system, if I choose both of our objects as our system, my F net going down this way is going to be Fg2. I could add tension, but notice tension goes with the acceleration, and also it opposes the acceleration, which really doesn't do anything to accelerate my system at all. But I also have Fg1. Fg1 is opposing my direction of acceleration. It's going in the opposite direction. So this one I actually have to subtract. I have to subtract Fg1x, but only the x component, not the entire weight, because only part of the weight is doing the pulling down part. And so this is equal to my m total times the acceleration of my whole system. My t's go away, of course. So let's put a few things in. We know that Fg is equal to mg, so a few things can be substituted in there. And I also know that Fg1x I already found over here, so let's do some substitution here. Fg, I'm going to have m2g, and this is going to subtract F1 times sine of 35, and this is going to be equal to my m total times the acceleration. And again, I am going to substitute this guy in here as well, instead using m1 instead. I'll have m2g minus m1g times sine of 35, and this is equal to the total mass, m1 plus m2, all of it times acceleration. We're going to solve for acceleration by dividing both sides by m1 and m2. So be careful, even though you're tempted just to cross out m1 and m2 because you have m1 and m2, you still need to make sure that you divide everything by the sum of the two. Algebraically, they don't mean the same thing. So I have acceleration is equal to m2g minus m1g sine of 35 all over m1 plus m2. Putting in all our values, we have m2, which is our 4 kilograms, times 9.81, minus our mass 1, which is our 6 kilograms, times 9.81, times sine of 35, and all over 4 plus 6, which is 10. So let's put all that into our calculator. So it seems like I made a very lucky guess, and that the acceleration turned out to be positive, which means it indeed, my entire system does indeed accelerate towards the right and down on the right. So, and the value that I got is 0.5479, which is going to round up to 0.55 meters per second squared down on the right. Now, if you had assumed that the object went in the opposite direction, let's say you assumed that it goes in the opposite direction, you're going to still get the same number that I did, but except it will be negative. And if you get that negative sign, it just means that your whole system will be accelerating in the opposite direction. You do not need to fear the fact that you had to make an assumption, because your problem, how you set everything up, is going to self-correct itself at the very end. I just got lucky in assuming the right direction. So notice that doesn't matter whichever mass is larger, it also depends on the angle of the incline, because if you think of it this way, if this incline is anything bigger than 35 degrees, then the 6 kilogram mass is going to have a larger Fg component going down the incline, meaning my whole system could be going down towards the left side, depending on this 35-degree angle here, whether or not it's bigger or smaller. So sometimes it's just much easier just to go ahead with the problem, make an assumption, and self-correct yourself at the end, as opposed to calculating whichever force is larger to make that decision for yourself. So that is kind of how you could tackle question A with acceleration of the masses. Because now what we can do is tackle B, which is finding the tension in the rope. When we're finding the tension in the rope, you learned from previously 3.06 based on tension that it is much easier to change our system to not using two, but only using the one system, using the one object as your system. And because I really want us to practice looking at inclines, even though I know mass 2 is going to be easier to analyze, I'm going to choose to analyze mass 1 so I give us a little bit more exposure to dealing with incline problems, okay? So I'm going to look at my system being mass 1. So mass 1 is my system, okay? So if I take a look at mass 1, I'm going to look at my F net. And I know now that my mass 1 is going to go up the incline based on my previous assumption, and it worked out. The F net is going to be up the incline. This is equal to m1 times the acceleration, which we already know from the previous question. And we're going to look at the F net along the x-axis. So I'm going to make that note just so we're clear. We're looking along the x-axis because that's how we find tension. Tension is acting along the x-axis. So along the x-axis of mass 1, we have tension. We also have Fg1, which is also acting along this axis as well. Now notice tension is pulling it up in the same direction as acceleration. So here my F net is going to have to include tension being positive in the same direction as acceleration. My Fgx is opposing the direction of acceleration, which I will write Fg1x, where I'm going to subtract it. After that, those are my only two forces, so I end it by equating all of that to ma, mass times acceleration. If I solve for T, my tension, I just have to make sure that I completely isolate it on one side of the equation so that I am left with T is equal to mass 1 times acceleration minus Fg1x. And I know Fg1x is Fg1 sine 35, or I can say that this is m1g sine 35 because Fg is mg, right? So I'm going to write here instead ma or m1a minus m1 times gravity times sine 35. So let's calculate this out. We have mass 1 as being 6 kilograms, I believe. So this is 6 times the acceleration, and of course I'm going to use a non-rounded value, 0.5479, 0.5479, meters per second squared, minus mass 1 again, which is 6 times gravity, 9.81, and times sine of 35. So after I put this in the calculator, I will get the following. Oh, sorry, and I forgot one thing, that because I added on this side, this should be a positive sign, this should be a positive sign, this over here should also be a positive sign, giving me a total of 37 newtons as my tension. So here is an example where we've dealt with a combination of tension problems, multi-body problems with inclines, all together as one kind of problem. So notice that we could have also used mass number 2 to also solve for tension. That could have, if you did that, that would have worked as well. You also would have gotten 37 newtons, but I decided to use M1 just to give us some extra practice looking at inclines, on objects on inclines. So hopefully you got something out of this video. And always draw your free body diagram. Always have making sure that your forces that are in the same direction of acceleration is positive, the ones that are opposing it are negative, and knowing how to fully use your free body diagram to write your F net equals ma equation. So, hopefully you enjoyed this video, and again, please practice, practice, practice. Practice will always make it better for you, okay? So, hopefully you enjoyed this video. Thank you for watching, and stay tuned next time for more videos on physics. Good luck.